Okay, in this video I'm going to talk about qualitative heat problems, also known as LOLs. Qualitative meaning we're just talking about where the heat's going in or out, as opposed to quantitative, which is doing mathematical calculations. Alright, so the first example, we have a glass of cold water heated from 0 Celsius to 80 degrees Celsius. So the first thing we have to determine is how many LOLs we're actually going to need for this problem. To do that, you should sketch a very quick heating curve. 1, 2, 3, 4, 5 parts. And every time there's a new part in the problem, a new section of this graph, you need a separate LOL. So in this case, if I'm starting with 0 degrees Celsius water, it's going to be down here. And if I'm ending at 80 degrees Celsius water, it's going to be here. So in fact, you can see here, we're only dealing with one segment, just the warming of water. We're not dealing with any kind of phase change, so we just need one LOL. Okay, so L, O, L. Now at this point, let me just say that if you're not one of my students, your teacher might have little differences in these. Go by what your teacher says, not by what I say. We all do these generally the same way, but there might be a couple little things here and there that are different. Anyway, first thing I want to do is just fill out my O. So in this case, I'm just going to say H2O for water. This just gives us a perspective, because I could ask you to give me an LOL from the room's perspective or from the glass's perspective, and those are actually going to be different, the opposite direction. Okay, so once we have that down, I want to identify where I'm starting from and where I'm going. Well, I'm starting with 0 degrees Celsius liquid, and I'm changing that into 80 degrees Celsius liquid. Okay, so my first column, ETH, then I have EPH. ECH, I'm just going to leave out completely because there's no chemical change happening. Okay, and just as a reminder, thermal energy is energy that's going to be associated with a temperature change. So when the temperature is going up, thermal energy goes up. When temperature stays constant, thermal energy stays constant. Phase energy is the energy locked up within the phase, within the state of matter. So just by existing as a solid or liquid or gas, the particles are going to have a certain amount of energy. So unless the phase changes, EPH is not going to change. Anyway, I always start with EPH because it's very set in stone. For liquids, we're going to do 2 bars. That's just like 2 bars. It's just like 2 whoosh lines for a liquid. And it's a liquid after, so again, 2 bars. Now for my thermal energy. The rule of thumb that I use is room temperature water, I like to think of as 2 bars. If you're cooling it down and you get to 0, that's 1 bar. If you go below 0, like dealing with really cold ice now, that's like a fraction of a bar, so like half a bar, something like that. If you're, again, starting at room temperature 2 bars and you're warming it up, once you get around 100, that's when I like to use 3 bars. Anything above 100, we're now dealing with vapor being heated, that's 4 or more bars. This is all kind of relative. As long as you show a change in the correct direction of heat, I don't think your teacher's going to mind if you use 3 bars whereas they use 2, anything like that. So I have 0 degrees Celsius. I'm going to give that 1 bar of thermal energy, and that's heating up to 80. Now I said I like to use 3 bars for 100. Well, this is pretty close to 100, so I'm going to use 3 bars for this. Okay. If you choose to do like 2.5 here or even 2, that's fine. We're going to get the same answer in the end, just a different number of blocks. Okay. So I have 3 total blocks of heat in the water initially, 5 total blocks of heat in the water finally. The difference is 2, so I'm going to draw my 2 blocks kind of halfway out of the water. And I need to say, is this heat going into the water or is it going out of the water? Well, since this is the water, it had 3 and now it has 5, heat must be going in. And we can kind of wrap this up by writing endothermic. That's because heat's coming in. So this is how I would draw the LOL for this problem. Next and final problem I'm going to do in this video, a glass of water is put in the freezer and reaches negative 10 degrees Celsius ice. Okay, so again, let's just quickly sketch our cooling curve in this case. Not a heating curve. Since we're cooling it down, it's going to be a cooling curve. 1, 2, 3, 4, 5. So I'm starting with, well, I just say a glass of water. I could have been a little more clear there. but that's kind of up to you. I'm going to call it room temperature water. I'll call it about 25. You can call it 20. If you want to call it 100, that's fine. It's up to you. So 25 degrees Celsius water, that means I'm going to start right about here. And you're going to put it in the freezer, so it's going to completely freeze, and it's going to turn into negative 10 degree ice. So now I have segment 1, where the liquid's going to cool down, segment 2, where the liquid's going to freeze, and segment 3, where the solid, which starts at 0, is now going to drop down to negative 10. So I'm going to need 3 total LOLs. 1, 2, and 3. Okay, let's start with the first one. So this is in the perspective of the H2O. I like to use H2O instead of water because when you're dealing with ice, it's not really water anymore. So H2O works for all 3 states. Okay, ETH, EPH. Let's write our starting point. So I'm going to say we're starting at about 25 degrees Celsius liquid. And this is going to drop in temperature until it reaches 0 degrees Celsius liquid. We're not going to say that it freezes yet. The freezing is its own separate step. So don't put solid here. Okay, liquid gets 2 bars of phase. Liquid gets 2 bars of phase. Now for thermal, I'm going to give 25 2 bars. And I'm going to give 0 1 bar. Difference is 1 bar, which is going out of the system, exothermic. So that's just step 1. Step 2, H2O, ETH, pH, ETH, pH. Alright, so our water has now reached 0. So our starting point is 0 degrees Celsius liquid. During this LOL, we're going to be freezing the water. So it's going to turn into 0 degrees Celsius solid. Remember, no temperature change during a phase change. Okay, there is my liquid, 2 bars of phase energy. Solid gets 1 bar of phase energy. My initial temperature was 0, which I said was 1 bar, and my final temperature is 0, which is also 1 bar. Okay, one quick thing you want to check if you're doing this correctly. If you're doing like a multi-step problem, this one here should match the one before it. So this bar graph should look like this one, and it does. Okay, so the difference, we have 3 going down to 2, so I have 1 bar going out, exothermic again. Finally, my last LOL, we're still dealing with H2O, ETH, EPH, ETH, EPH. So we've now reached 0 degrees Celsius solid, or ice, and that's now going to cool down to, let's say negative 10. Yes, negative 10 degrees Celsius. Where did that go? I didn't delete that, did I? Oh, there we go. So it's going to go down to negative 10 degrees Celsius, ice, or solid. Okay, let's fill out our LOL here. So solid gets 1 bar, solid gets 1 bar, 0 degrees gets 1 bar for thermal, negative 10, now I'm dealing with really small temperatures, so I'm going to go with a fraction of a bar, about half. So the difference here is about half a bar. This is also going out because it's being lost, exothermic. Okay. So that's a 3-step LOL problem. Last thing you want to check, exothermic, exothermic, exothermic. If you're doing a multi-step problem, they should all be the same, either all endo or all exo. That's how you do LOLs.